Hello, welcome to everyone to the first quantum session of the MECO conference. It's a great pleasure for me to introduce Paola Ruggiero, who is currently lecturer at King's College London. Paola did her PhD at CIS and after that did a postdoc in Geneva and since 1 year is at King's. So she will tell us about entanglement and disorder in many-body quantum systems.
Thank you. So thank you very much for the invitation. First of all, it's a pleasure to be here to this conference organized mainly by my new collaborators in the group. Actually, it's the first time that I meet in person Pier Paolo, but okay. But it's very good. It's very good to finally be here. And yes, today I'm going to talk about entanglement and disorder in many-body quantum system from a renormalization group perspective. So this is a bit different from what we heard in the morning, but hopefully I'm gonna make it clear. And let me start with some motivation. So why are disorder many-body system interesting? So the main reason is that the disorder turns out to play in the realm of many-body quantum world. Basically gives rise to many interesting phenomena, and this is already true at low energy, meaning when looking at ground state properties. Because in this case, so just to mention some example, one can find interesting phenomena on like a Kondo effect. We're looking at how electrons interact with the impurities in system, or also, as I'm gonna tell you something more about later, gives rise to exotic phases of matter. But it's probably even more interesting when looking in the middle of the spectrum, namely when looking at out of equilibrium physics. And here probably the most, arguably the most interesting example is Anderson localization, namely the fact that particles within a random, so subjected to randomness, don't move because they are localized indeed. And so the Anderson localization is how we define this phenomenon in the case of free particles. But then when we come to interacting systems, then this phenomenon is known as many-body localization and is a bit less understood, but it has some interesting properties which are associated to mainly ergodicity breaking, namely the fact that the system does not really thermalize. And this is usually understood as coming from an underlying integrability, namely the fact that there exists an infinite number of conservation laws in the system. Other interesting properties are suppression of transport and a typical logarithmic growth of entanglement that I'm going to discuss later on. And in fact, the other keyword of this talk is entanglement. And also here, you're allowed to ask yourself, why should you care at all? And also here, I mean, there are several reasons for doing that. The main being that entanglement being really at the heart of quantum mechanics turns out to play an important role in many physical situations. Okay, okay, as I mentioned before, in the case of disordered system, entanglement turns out to be a good indicator of localization, but also more generally, entanglement is a which I will define, I mean, better in the next slide, but it's just a measure of quantum, roughly speaking, is a measure of quantum correlation. And this allows to detect different phases of matter as, for example, topological order, but also distinguish between different phases, as, for example, behaves differently in Anderson versus many-body localization. It's also used to probe quantum criticality and therefore the existence of phase transition, because it is known to show universal scaling properties at the phase transition. And actually, in a very different context, is also very important, like in black hole physics for high energy physicists, even if we don't have many here, I guess. Because black holes are known to carry an entropy known as Bekenstein-Hawking entropy, and this can be kind of understood in terms of entanglement between the degrees of freedom inside and outside the black holes. But from a more pragmatical, maybe viewpoint, entanglement has been crucial for the developing and understanding of numerical algorithms, in particular those based on a tensor network and matrix product states, and in quantum computers. So in particular today, I mean, we are kind of in, so we can talk about these NISQ devices, which are we are in the era of noise intermediate scale quantum computer, where entanglement can be generated and manipulated. Okay, so this is just to give you a bit of a flavor why one should be interested in such quantities. And so here comes the first issue when you want to study entanglement in many-body quantum system, which is, so how do we quantify it? So first of all, let me recall it, the definition, which is the following. So consider a generic system and the bipartition of it in this way into a subsystem A and the rest B. And assume that this induces a bipartition of the Hilbert space, okay, where the states live as a Hilbert space associated to A and one associated to B. And so what we mean by a state, generic quantum state psi to be entangled is just that it is not of this form. So it cannot be factorized as a product, tensor product of a state into A and the state into B, okay? However, while, I mean, this seems quite a clear definition, this does not tell us how much entanglement is in that state. And in fact, I mean, it's not, the reason is that it does not exist a unique tape, so to say, of entanglement. So one has to quantify it some way, meaning defining quantities that, I don't know, grows when quantum correlation grows and so on. So it has to ask for a certain number of properties. I'm not going through that, but many physicists, in particular people in the quantum information community, worked a lot on that and introduced many quantities that have such a goal. And in particular, in the following, I'm going to focus on a number of them. So a crucial quantity to introduce most of the quantities I'm going to be looking at is the so-called reduced density matrix. So if we start in our the total system is in a pure state of psi, so we consider the associated density matrix, which is an operator constructed in this way, the cat and the bra. And then the reduced density matrix associated to the subsystem A is obtained by the total density matrix rho by tracing over the degrees of freedom of B. Okay, so now this object lives in the subsystem A, and now given this object, arguably the most important quantity that one can look at is the for Neumann entropy, which is just defined as the minus trace of rho A log rho A. And this is, in fact, was proven to be a good measure of entanglement in the case of pure bipartite system. What I mean is just that the whole state is in a pure quantum state, okay? And more generally, one can introduce Iranian entropies, which are labeled by a real positive number alpha, and they are defined in such a way: 1/1 minus alpha trace of rho A to the power alpha. And so they have less good properties than for the Neumann entropies, but still sometimes they are easier to compute. And in the limit of alpha going to 1, we recover the for Neumann entropy. And another, so if we are now interested in more generic situations, so say that now we have some multipartite system in this way, and we are interested, for example, in the entanglement between two non-complementary subsystem A1 and A2, say. Now it turns out that since basically now the starting point would be to consider the reduced density matrix associated to A1 union A2. So this will be in general associated to a state which is not pure, so a reduced density matrix, a more general state. And therefore, in this case, it turns out that the for Neumann entropy is not a good quantifier of quantum correlation. And this is just because basically it's not able to distinguish classical versus quantum correlation. So it will just contain information about quantum correlation, but also, I don't know, thermal fluctuation and stuff like that. And so in this case, one can introduce other quantities, and in the following, I will talk about this logarithmic negativity, which I mean, one can introduce many quantities, but this is good quantities because basically it can be computed in some specific case for a many-body quantum system. Because I mean, at least it has an explicit formula, okay, so which does not involve some minimum or maximum, which in general makes it even numerical hard to compute. Just to give you an idea, even if I don't want to go really in the details, so this is defined in terms of an operation called the partial transposition. So the idea is that one starts with the reduced density matrix associated to the subsystem A1 union A2, okay, and then perform this this operation, which is called partial transposition. So if AI1 and AJ2 are bases into the two subsystem A1 and A2, so the idea is that we only transpose the degrees of freedom within one of the two subsystems, A2, say. So this is not very intuitive, I can understand as definition, but the idea behind that is that now this partial transpose object is not positive definite anymore, as it was the case for the reduced density matrix. And the presence of negative eigenvalues so was shown to be a good signature of the presence of entanglement. So this quantity basically is just defined in order to capture the presence of these negative eigenvalues. All right, so this is a bit the dictionary. So this is these are the quantities that I'm gonna be talking about in the following. And let me start to talk about a bit about entanglement in disordered systems, starting from equilibrium. This is based mainly on some work in collaboration with people at CISA and people in Madrid. All right, so and as a prototypical model, I will focus on such model, which is basically the XXZ spin chain. So so basically these are just the Pauli matrices, okay? So in the Y, X, and Z direction, and basically this is a one-dimensional chain. Delta is an anisotropy parameter, but what is important is that now the overall constant Ji is a random variable, okay, and is drawn from a given probability distribution. Now, of course, the model, because it's interacting, because this basically what I mean by interacting is that this can be, if delta is 0, this model can be mapped to free fermions, and so is basically free. But when delta is different from 0, is mapped to interacting fermions. So the model is interacting, and because of disorder, so basically because these Ji are not uniform, or not just the same at each side. So the system has not even translational invariance. This system is hard to solve exactly analytically. And so I will rely on a technique which is known as a strong disorder renormalization group. So the idea is, it's similar to a standard renormalization group, let's say. Basically, our model will be a point in a theory space, okay? Usually the theory space in standard renormalization group is defined in terms of the couplings. Here, basically, you can think of your model as defined by the Hamiltonian and the probability distribution from which your couplings are drawn. So you can think to a generalization of your theory space where on the axis you don't have the couplings themselves, but their probability distribution. Okay, this is just a picture if you want. This means that each of these direction has infinite dimension itself. But your model is somewhere inside here. And basically, similarly to a renormalization group, what you do is that you can define a decimation procedure. And this decimation procedure will make your coupling Ji flow, okay? And in turn, this will make your probability, the probability from which they are drawn, to flow as well. And therefore, this really defines a flow, which is an RG flow. And to be more specific, if we now go to logarithmic variables. So your ji becomes beta I, okay, logarithmic variables, and this is the maximum of your ji, which fixes an energy scale, which is basically your Rg time. And in terms of these variables, we can now write an equation, a flow equation from the probability distribution of our couplings, in our case for the J's. And the crucial point is that for a class of models which include the XXZ spin chain, this equation was proven to have a unique solution, okay, independently on the initial. So independently on the initial distribution of the J, this means that we will flow to a same probability distribution, so which is known as so this point is known as infinite randomness fixed point, and the distribution at the fixed point looks like that, or so in the original couplings is basically a power law, okay, power law distribution. And another consequence is that at the infinite randomness fixed point, our state it is approximated by the so-called random singlet phase. So the model itself will have a complicated ground state, okay? But in this RG approximation, what this RG procedure tells us is that the state itself can be approximated by a bunch of singlets. So each bond here just represents a singlet like that, okay? So two spins join a singlet. And so the state is just approximated as a bunch of singlets, which you can just connect to spins which are arbitrarily far away. Okay, so this is actually quite old work. Where was introduced in the 90s by Dasgupta, and the existence of this fixed point, this unique fixed point, was proven by Fisher in the 90s. But actually, it took a while to understand how to compute entanglement, and the reason is the following. So now say that you want to compute the entanglement entropy, the von Neumann entropy of an interval A, okay, in an infinite system. So now, and you want to compute that in the ground state. So now in this approximation, this is how your state look like, and so it's easy to understand that. So entanglement can only be generated by those singlets which are shared between your subsystem A and the rest, right? So nothing else basically creates correlation with it within the system. And so for a single disorder realization, so for a given random singlet phase of this form, it's clear that the entanglement entropy is just given by the number of singlets which are shared times log2, which is just the entanglement entropy associated to one of such singlets. Now, what is complicated instead, so this is a kind of trivial, right, at this point. So, but, and this is why, by the way, this is a very good framework to study entanglement. But what is difficult instead is to compute the average over many disorder realization, which is what is meaningful in this disorder setting, right? Because now we are going to have such a random singlet phase for each disorder realization, and we want to compute the average over them, and we want to see, for example, how it scales with the size of the subsystem. So this is actually a non-trivial calculation which was performed only in 2004 by Raphael and Moore, and we showed that basically this number of singlets scale logarithmically with the size of the subsystem, and this is and they also were able to fix this prefactor. Okay. All right, so what we did some years later is basically to wonder, okay, what about some more complicated setting? So now if we are interested in the logarithmic negativity, namely we are interested in the entanglement between two non-complementary regions, okay, A1 and A2. So now, again, for a single disorder realization, it's clear that entanglement between these two regions can only be generated by singlets which are shared among those, right? But now it's not that trivial actually to, again, via strong disorder RG to compute the average over disorder of this number of singlets shared by two non-complementary regions. Okay, this is the difference between before. But anyway, this can be basically what we did is to relate this calculation to the previous one. We were able to get the scaling also of the logarithmic negativity in this case. And again, we find that this scale logarithmically with the subsystem size. So it's actually there is a nice observation. So for those of you which are more familiar with quantum system, but more in the translational invariant setting, probably you notice that this is exactly the kind of scaling that this logarithm of L and logarithm of this ratio is exactly what you would find for the XXZ spin chain, let's say, but for a clean system, right? And so one can, and actually, for example, this can be understood usually using conformal field theory arguments. So one can wonder, okay, so how comes? Yeah, we have disordered systems, so it's completely different. We don't have any of such symmetries. Why do we find such a behavior? But actually, the reason is that such log behavior is, after all, related to some scaling variance, some underlying scaling variance. And here, even if for a given disordered realization scaling variance is clearly broken, when we average over many disordered realization, then we kind of recover this scaling variance, but not conformal invariance though. But I mean, scaling variance is enough to recover this logarithmic behavior. All right, and so actually, this logarithmic scaling that we found is quite peculiar because there is, let's say, a strong belief, okay, that ground states of physically reasonable Hamiltonian, let's say in a proper sense, satisfy rather an area law. What this means is that basically, if we have a bipartition of this kind in A and B, we expect the entanglement to scale as the boundary of A rather than its volume, for example, for ground states. And so in one dimension, what this means, so we have such a geometry, right? So what this means is that we expect the entanglement just to saturate to a constant, because the boundary here is just a bunch of points, two in this case, okay? And so we see that, so what we found instead is that in these random spin chains, we have a dependence on the subsystem size L. So the entanglement actually does not saturate, but grows logarithmically with the subsystem here, and so that's violating this area law. However, this can be understood as follows. So in one dimension, this physical like belief becomes more mathematically grounded, let's say, and is actually a theorem. This is a theorem due to Hastings in 2007. And of course, as any theorem, it has some assumption, right? And so this area law is found to hold for Hamiltonian which are local, which are gapped, and which are translational invariant. And therefore, we see that in our case, what we are violating is exactly translational invariance, okay? That's why we can actually violate in one dimension this area law. And actually, using strong disorder RG, one can play around and actually found many quite exotic violation of this area law. So what I discussed before was this logarithmic violation of the area law, which is found in these random spin chains. So another extreme case is actually one where one can get a volume law, okay, in a model which is of course constructed a bit ad hoc, but so this is called the rainbow model. And in practice, it's a model with no disorder, but which is inhomogeneous. So basically, it's kind of the XX spin chain where the couplings are decay exponentially from the center. So it is inhomogeneous. So again, it breaks translational invariance. And again, this can be the ground state can be approximated in this RG sense with the random phase, but we see that it's a peculiar one where so all the bonds are concentric around the origin, and so this gives a volume law for the entanglement entropy. And okay, just playing a bit around, what we realized more recently is that if you now consider a model which has both randomness and inhomogeneity, which we call a randbo, okay? So you can have actually an intermediate phase and find a square root violation of the area law, which can be actually understood in terms of constrained random walks and stuff like that. But I don't want to go into that. This is just an idea to say that this strong disorder RG actually gives a very powerful way to understand entanglement properties in this disorders system. But as I was saying at the beginning, so even more interesting is when we go out of equilibrium, right? So here we expect even more interesting stuff happening. And about that, I'm gonna discuss about a recent work in collaboration with Jack Turkeshi, which is here. And all right, so the starting point is again a strong disorder normalization group, and actually a time-dependent one. So in this very cryptic paper to me, actually, of but actually very very well-cited paper by Bosk and Altman in 2013, they introduced a time-dependent extension of the strong disorder normalization group, where so first of all, let me say that again, I'm going to focus for concreteness on such protocols. So I'm going to start in a state which is a product state. Okay, so in particular for definiteness, I can focus on the null state, so just alternating up and down spins. And I will let them evolve with the disorder XXZ spin chain, which I showed you before. And now, again, one can define energy procedure as before. The main difference being that now, so usually when one does RG, the idea is that one integrates out degrees of freedom which are high energy, right? In order to just remains with low energy degrees of freedom. Here, instead, we just want to integrate out through our decimation procedure degrees of freedom which are not relevant for the dynamics. That's the idea, okay? And this can be done in some proper sense using perturbation theory. And basically now the target, instead of being the ground state, which we're getting before, will be the state at time t. This is our new target. The main thing that changes, so basically what these people show is that you basically get exactly the same flow equation from the probability distribution of your couplings. So exactly the same as an equilibrium. So again, this they call a dynamical fixed point, but it's exactly the same infinite randomness fixed point that I showed you before. The only difference being that now the energy scale, so the RG scale, which before was related to the energy scale, right, of our system, is instead directly related to real time, okay? And this can be naively, let's say, understood as an energy time Heisenberg relation. All right, and the picture, anyway, so here I just give you an hint of what's the idea behind this method. The idea is that now, basically, the picture which comes out is the following. So as long as interaction do not play a role, our random singlet phase is basically replaced by a dynamical version of that, where basically, again, the state at time t is again of this form, okay? It's just a product of pairs of spin, but now the pairs, rather than being singlets, will be oscillating pairs like that, okay? What happens, however, due to interaction, is that at a certain point, which is a certain time, which depends on the strength of interaction, so delta here, so spins will start to talk to each other, and so basically some cluster of spins will start forming, okay? So that we cannot just consider a product of pairs, but we have to consider more complicated structure, which are clusters. Okay, so this is a bit the idea that is what we need for the following. And again, so what these people studied was basically they gave prediction for the von Neumann entropy, and so which work as following. So in the non-interacting case of as long as delta is equal 0, basically what I said before is that the singlets are replaced by oscillating pairs, but apart that we have exactly the same picture as at equilibrium. And therefore, the computation is exactly the same as at equilibrium. So now, again, the entanglement entropy is basically related to the average number of singlets shared between a subsystem and its complement times the contribution now of an oscillating pairs, which can be estimated as an average over time over one period of oscillation. And now, as before, this number of singlets scales in time as log gamma, where this gamma before was related to the subsystem size, and now, as I said before, is related to real time instead. And basically, this is such that we find basically, so this gamma behaves in this way. So at the beginning, it just grows as gamma of t, which I remind you, it was growing as log t. So basically, we are saying that at the beginning, this entanglement will grow very slowly as log t, okay? Because because basically here we have a log here, and gamma itself goes as log t, so it's a double log of t. And then eventually, of course, we expect that to saturate, okay, to a value which depends, of course, on the system size L. Now, if we move to the interacting case, actually things, of course, gets much more complicated. But here I present how this author were able to provide at least an estimate of the growth of entanglement. So the idea is that now basically these oscillating pairs in the interacting case gets replaced as independent units by these clusters of spins. So now basically say that in the early time regime, where still early means exponentially large times, but still early, this cluster, which here I just represent as this box here. So as long as these are much smaller than the subsystem size A, so basically we expect that the contribution to the entanglement will just come from the cluster which go across the boundary of this subsystem. So for example, in this example here will be just 2, right? Because we have two boundaries. And therefore one should basically estimate the entanglement associated to one of such cluster. And this is estimated as follows. So this BAAC is just the number of bonds of the subsystem, so 2 in this case. And this d0/2 is basically the contribution to a given cluster, which is estimated basically as the average entanglement of a random state, because you expect that basically by evolution you will just entangle a lot these spins, and so you can estimate this as the entanglement of a random state. But then you take into account that because of the constraint given by your initial state, you will maybe explore just half of your Hilbert space, and so this is what you get. So this 0t is basically the average dimension of the cluster. And so yeah, I'm just using that basically a class. So the entanglement of a cluster is given will grow as a volume law. Okay, just this is just the usual. This is a result, all the result by page. And here the volume law is just related to the volume law is just given by the dimension of the cluster, and the dimension of the cluster, of course, depends on time, because this cluster will grow and grow in time, and this can be estimated, and this is what is done in this paper. And basically, what they found is that the size of this cluster grows logarithmically with the power which actually depends on the initial state. And what is interesting is actually that so in this way they give a kind of analytical argument of this logarithmic role of entanglement, and so they kind of argue that this many value localization can be understood as a dynamical RG fixed point. Then, of course, at intermediate time, they cannot say much, but what they can say instead is that so when basically the dimension of a cluster becomes comparable with the subsystem size, they cannot say much, but eventually, of course, we expect the entanglement to saturate because the subsystem is finite, and it will saturate to an extensive but not thermal value. That's what they claim. All right, so based on that, I mean, based on this picture, this RG picture, now we are able, and this is what we did with Jack, is to study other quantum information quantities, basically. So now can one, for example, look at the logarithmic negativity, and as before, as long as we are in the non-interacting regime, the calculation basically works exactly as at equilibrium, right? And so now again, we are in this situation. So where now this links has to be understood as oscillating pairs rather than just singlets. And basically, again, the negativity will be given by the number of these pairs shared by the two subsystems of interest times the contribution of a given pair. And this contribution of a given pair, again, can be estimated by looking at the average over time over one period. This is what we did. And this is what we did. And basically, so this, and now the average number of singlets basically gives this behavior shown in this cartoon. So it will have, so at the beginning, if the two systems are disjoint, it will be 0 up to the distance between the two subsystems R. Then there is a double log growth. This is a double log scale growth. Then there is a first plateau. Then the entanglement decreases, and then it saturates to a given value. And then this is an interesting prediction, because actually from simulation it's very hard, even for this non-interacting case, to get this. And in fact, here what we show here is that what we can get is at most this first logarithmic growth, but we cannot get the rest of the curve. Okay, but the first logarithmic growth seems to kind of agree with this prediction. And in the interacting case, again similar to before. So if we are interested in the entanglement between these two guys, so for as long as the clusters are much smaller than the subsystem size, so there will be entanglement between the two only if there is some cluster which cross between these two subsystems. So in this case, for example, will be just 0. But if the two subsystems were attached, there will be one cluster in common, and this gives the same prediction, and so the same logarithmic growth as it was for the entanglement entropy. And eventually, for very late time, we expect the negativity to go to 0. But again, we cannot say anything for intermediate times. And the last thing, so actually one can also, at the beginning, I introduced the Iranian entropies, right? So now, if we are interested in to look to the quantum information between two different subsystems, instead of the entanglement negativity, one can also look to the so-called mutual information, or actually it's a Rayleigh generalization. So this is basically given by the Iranian entropies of the subsystem A1 plus the one of subsystem A2 minus the one of the union of the two. And basically, this is usually a good quantifier of correlation, but again, it will count not only quantum, but also in general, also classical correlation. Anyway, we expect that this to be not so different from entanglement negativity as long as we only have bipartite entanglement, okay? So just keep that in mind. So following exactly the same discussion as before, one can actually very easily work out a prediction for the average over disorderization of these Iranian entropies. This is, again, in the non-interacting limit will be just the number of oscillating pairs times a prefactor, which is just the contribution of a single pair, okay? And so this is the prediction that we actually verified here. So now this slope will depend on alpha, but if we divide by this slope, basically we see a collapse of the curve. So this prediction seems to be reproduced by real simulation. And basically, I mean, given the Rayleigh entropies and this definition of mutual information, one can work out a definition, a prediction for the mutual information itself. What we find is that basically, when this alpha is equal 1, this coefficient is equal to the one of the negativity, and therefore we find this relation between this precise relation between the negativity and the mutual information 1/2. And surprisingly, this relation seems to hold also in the interacting regime, according to our prediction. And actually, this turns out that this relation seems to be quite general, because it was found also in many other contexts, going from integrable model to conformal field theory, and more recently in random circuits. So this seems quite a general relation. And yeah, so and this was more or less what I want to tell you. These are some more, just let me conclude with some more direction of what one can do with this strong disorder RG and its time-dependent version. So one is actually something interesting that we are looking at with Hubert Saler in Paris is the interplay between disorder and Kondo physics. Another interesting open question is about transport in the disorder and open quantum system. And even more interesting in particular, because there are nowadays experiments which studied that recently, is the dynamics in presence of symmetries. And we are something which we are doing with Jack. And with that, thank you all for listening, and particular thanks to my disorder collaborators. Thank you.
So thank you, Paola, for your nice talk. And we have time for only one question.
Thank you for this interesting talk. You spoke just about spin 1/2 models.
Yes.
Can you say something, thinking the value of the spin is different from this?
From what? Well, I mean, so we didn't, first of all, we didn't investigate that. So I don't think there is much in the literature. I know that at equilibrium, so for the first, regarding the first part of my talk, which was like in the ground state, there are works where people studied, for example, entanglement entropy. I think there is a work by Joel Moore and someone else. And already there, you understand that it's very complicated to generalize. So actually during my PhD, at a certain point, we thought about doing the negativity of that, but it was very, very complicated.